First, what is the fundamental theorem of calculus? Is actually discovered independently between Newton and Leibniz, which it is said that they argued over this fact. So the father of calculus is often referred to as Isaac Newton, but at the same time Leibniz is there as well. And actually our notation is Leibniz notation, and so a lot of the notation they use is based off of Leibniz notes. It is finding the area under a curve is what this is helping us do, this fundamental theorem of calculus. Guidelines for finding the fundamental theorem of calculus are listed there. You have to be able to find an antiderivative. So the whole goal of fundamental theorem of calculus is that you have an antiderivative. And then the definition here, or the actual theorem of calculus, is that if you are finding this integration, it comes from limit theory, but limit theory is not the easiest way to do it. Doing a limit every time is much more tedious. Using your summation, plugging in your summation, it's a lot more tedious. Doing the antiderivative is much easier, especially now that you know the rules of antiderivatives. And so the fundamental theorem of calculus says, well, just find the antiderivative, plug in your top limit to that new equation that you get, that new function, and subtract the bottom limit. Right, and so that's the fundamental theorem of calculus here. All right, you do not need a constant of integration. So if you look at these rules, you have to be able to find an antiderivative. You use this notation here, you're just subtracting the two, and you don't need a c, because when you'll see that will just go away. All right, you'll see that you would have a plus c here, a plus c there. When you subtract, the c's are going to cancel out, and the truth is you have a definite integration. They have given you everything you need to find this integration here, so you do not need the c. The c actually goes away in the process, and so you don't have to add a c when you're doing definite integration. You're actually finding a number. You're not finding a new function. Okay, so let's look at evaluating these. We are going to use our rules of antiderivatives here. All right, so we're going to use our rules of antiderivatives. So this first one, what we're going to do is we're going to find the antiderivative of this guy first. All right, and so I'm going to use my standard rule of finding it. I'm going to say, well, add 1 to my exponent and divide. So it's going to be x cubed over 3 minus, and then the constant's always going to be just times the variable. And I am going to go from 1 to 2. And that's how the notation is usually done. They'll have a little line from 1 to 2. And then you just plug it in. Plug in your 2. 2 cubed over 3 minus 3 times 2. And you subtract what happens when you plug in your 1. And that will be our answer when we solve it here. So we're going to take that, and we're going to say, well, 2 cubed over 3, that's 8 over 3 minus 6. So that's going to give us, what, 18 over 3? I just go ahead and get common denominators. And that's minus 1 over 3 minus 3 over 1 is going to be 9 over 3. And then I do them. Negative 10 over 3 minus negative 8 over 3 gives us a negative 2 over 3. And that is my answer. They sometimes get more difficult. So if you look at the next one, just rewrite it. 3x to the 1/2. You can pull the 3 out in front if you want to. So you can say 3, and then I'm going to take my integration here. So we have x to the 3/2, add 1. And if you divide by 3/2, you get 2/3 there. And we're going to go from 1 to 4.
So do you recommend?
Yeah, if it can't, so if you can see that it cancels, you can do that right there. Because this is going to cancel all the way across. And so I can plug in my 4. Square root of 4 is 2. 2 cubed is 8. 2 times 8 is 16. And then 1 cubed. Okay, good. 1 cubed times 2 is 2. So What is my antiderivative of secant squared?
Secant tangent. Tangent x plus c.
It's just tangent, right? So tangent of x from 0 to pi over 4. And they were nice, and they gave us one that does well. So I would say the tangent of pi over 4 minus the tangent of 0. Tangent of pi over 4 is
Square root of 2 over 2.
over square root of 2 over 2. So 1. And the tangent at 0 is 0. So my answer here is 1. Draw my tangent, which I'm pretty sure he looks something like that over and over, from 0 to pi over 4. Then I'm finding the area under the curve, right? And so between 0 and pi over 4. If I were to do this square root function, which looks something like that, right? From 1 to 4, they're saying that area here is going to be 14, all right? And so that's what you're doing really this whole time. We have a parabola here, you know, and so they're saying from 1 to 2, right? What is that area? And so you really start to get a picture of what are they talking about when they're talking about these things. So absolute value is a little bit different because you have to figure out if there's a turn in the function with absolute value. So what I mean by that is you need to figure out where it actually is negative and positive, because absolute value is always positive. And so you have to really set this guy equal to 0 and see if it changes from positive to negative somewhere in your interval. So like for this one, I would say, well, 2x minus 1 equals 0 at x equals 1/2. 1/2 falls in my interval from 0 to 2. And so I'm going to have to consider from 0 to 1/2, and then from 1/2 to 2. And so where is that negative? Well, if I plug in something smaller than 1/2, right? So I could actually write it this way. Where is it less than 0? It's less than 0, less than 1/2, right? So I know that from 0 to 1/2, this guy's going to be negative, right? I have a problem. Absolute value is never negative. So I'm going to take what's inside and say, well, I have to negate that guy. Because from 0 to 1/2, he's going to be negative, but it's absolute value. And so I'm going to negate that piece of it so that it will be positive. And then I'm going to take that, and this is where splitting it up helps. From 1/2 to 2, I'm good. It's positive already from 1/2 to 2. I don't have to worry about negating it. So I'm just going to do the regular function here. So with absolute value, you have to figure out where it is less than 0. And if it's less than 0 in your interval, you have to split your interval up. You have to change it to the opposite for the piece that would be less than 0, and keep it the same for the piece that would be greater than 0. But you do the integration the same. So I'm going to integrate this guy. And really, it might be easier to distribute that negative through. So negative 2x plus 1 here. I add an exponent 2 and divide by 2. This is going to be negative x squared. Plus add my x to that from 0 to 1/2, right? And then I'm going to do the same thing over here. This is just going to be x squared minus x from 1/2 to 2. I'm going to do those individually. So I'll take these and I'll say plug in a 1/2. So that's negative 1/4 plus 1/2. And this is nice because I'm just subtracting 0 here, right? So I don't need to worry about, normally it would be subtracting 0, right? That's my first piece of it. And then add to it 4 minus 2, plug in that 2. 1/4 minus 1/2 is my second piece of it. All right. So over on the left-hand side, I have negative 1/4 and positive 2/4 gives me a positive 1/4. Then I have 2 minus a negative 1/4. So I have 2 and 1/4, which is 2 1/2, or as they wrote it in the book, 5/2. Find the area of the region bounded by the graph y equals 2x squared minus 3x plus 2, the x-axis and the vertical lines 0 and 2. So what have they just said? Well, they have actually just given me an integration problem in words, which is very important to be able to decipher. Area of the region bounded by the graph. That means I'm going to integrate. Area of the region means integrate. Slope of a tangent line means to take the derivative. Area of the region means take the antiderivative. So they've given me the function of that. I'm going to do the function of the 2x squared minus 3x plus 2. So this is the function I'm going to integrate. And what is my boundaries? Well, they've told me x-axis and the vertical lines 0, that's my lower bound, 2 is my upper bound. So this is what it will look like right here. It will look like the integration from 0 to 2 of that function. And then I'm just going to take it. So how do I take the integration here? It's x squared. My new exponent is going to be 3. So it's going to be 2/3 x cubed minus my new exponent is 2. So 3/2 x squared plus 2x. And I'm going to do it from 0 to 2. So they've given me the function I'm differentiating. They have said area of the region, so that tells me antiderivative, function of the antiderivative, boundaries of the antiderivative.
So it didn't say area of the
Honestly, is plugging in and not messing up your numbers. So you're going to, what's nice when 0 is at the bottom, this is very important. When 0 is at the bottom, that's really easy because it's like minus 0, right? Especially if these are all x's, right? But when 0 is at the front, it's going to be 0 minus your stuff. So you have to make sure you plug it in. But when it's at the bottom, it's not a big deal. Plug in your 2. 2 cubed is 8 times 2 is 16. That gives us 16/3. Plug in a 2 again. You get 4 times 3 is 12 over 2. So that's just going to give us 6. And then we have plus 4. So this, of course, is just negative 2. 16/3 minus 6/3 is going to give us our 10/3 there. I figured it was just... Look at this one. So integration here, add 1 and divide by the new exponent. That's just going to be x cubed. Add 1, divide by the new exponent, add 1. All right, and we're going to go from 1 to 3. All right, so we're going to get the first group is going to be 27
That's what I did wrong.
plus, that was easy, 45 over 2 minus 12. And the second group is going to be 1 plus 5/2 minus 4. So then if you keep going, 27 minus 12 is going to be 15 or 30/2 plus 45/2 minus 1 and negative 4 is going to be negative 3, so negative 6/2. So this is going to be negative 1/2. So you have 74/2. Is that what I said? No. Yep. So it's going to be 76/2, which is 38. So the mean value theorem and average value function really go hand in hand. Mean value theorem is the theorem behind it, and average value is kind of how you solve for it. If f is continuous on the closed interval AB, then there is a number c in the closed interval AB such that the antiderivative from a to b equals f of c times b minus a. And so they're just saying there is some function that's going to be right there at the same value there. And they give this picture here of the mean value that somewhere in there you're going to get the exact average there, just like we talked about for derivatives. And so if you look at average value of a function, then how do you figure out that that is true? How do you find that? You do the antiderivative from a to b of your function, and then you just multiply by the reciprocal of that subtraction. So you basically divide by the difference. So once you're done with that antiderivative, divide by the difference of those guys. And you can keep this fraction out here on the outside the whole time, and then just do it at the end. So you would take the derivative the way you normally would, or antiderivative the way you normally would, and just do that at the end. So here's the example of that. Find the average value of the function 3x squared minus 2x on the interval 1 over 1, 4. And so On the outside of this, if they want average value, you're going to say 1 over 4 minus 1. That's what you're going to do for 1 over b minus a. And you're going to take the integration from 1 to 4 of 3x squared minus 2x dx. You're going to do this guy exactly how you would. Antiderivative, you add 1 and divide, so this is going to be x cubed, minus add 1 and divide, that's going to be x squared. You're going to do that from 1 to 4, but you're going to multiply this whole guy by 1/3 because of that when you're done. So you do the same thing, you'd plug in your 4. 4 cubed is 64, minus 4 squared is 16. We're going to take that upper bound, subtract our lower bound. 1 cubed is 1, minus 1 squared is 1, which works out nicely because that doesn't really do anything. 64, and don't forget you are multiplying this whole thing by 1/3. 64 minus 16 is 48. So you get 48 times your 1/3, 48 thirds, which is perfectly 16. That is your average value over that function. Your average value over the function is going to be 16. So if you look at the top of page 281, when we define the definite integral of f on the interval a, b, we use the constant b as an upper limit, and x is the variable of integration. So now they're going to look at a little bit different situation where the variable x is an upper limit, or some function of x is an upper limit. It actually doesn't even have to be x itself. And so instead of going from a lower limit constant to an upper limit constant, you go from a lower limit constant to a function. And they show the function here, example 6. Evaluate this from 0 to x at x equals these 5 different situations. If I were to take this integration, the antiderivative of cosine is sine, right? Because we're going backwards. So antiderivative of cosine is sine. So we have the sine of t. We're going from 0 to x. Well, that's going to be the sine of x minus the sine of 0. Well, the sine of 0 is just 0, so this is just the sine of x. And then they want it for these 4 things. Well, you just plug it in. Sine of 0, sine of a 30-degree angle, sine of a 45-degree angle, sine of a 60-degree angle, sine of a 90-degree angle. And so you get these individual answers here. Square root of 3 over 2 And that is just going to be 1. And so you have different functions there potentially. The first fundamental theorem of calculus actually says that if you have a function at the top of it, so if f is continuous on the open interval I containing a, then for every x in the interval, if you want to go from a to x of that function and find the antiderivative and then find the derivative, it's going to end up being just that function at x, which seems counterintuitive, but they're saying if you take the derivative of the antiderivative, you get the function inside. There are some caveats to this. We're going to look at ones where it's not just an x at the top. But really the derivative of the antiderivative is going to be original function is basically what. For this one, it wants me to take the derivative of the antiderivative. Well, if my top value here is an x, I don't even have to do that. I just need to plug an x in for this. Because if I take the antiderivative and then take the derivative back, I'm going to end up with where I started. It's almost like inverse functions. And so for this, you really just have to take the x and plug it in for your t. And your answer here is going to literally be what the inside guy with the x plugged in. That is my answer. Pretty straightforward. There can be situations where you don't just have a simple x here. You have an x cubed. When this happens, the constant down here actually doesn't matter. He's not going to affect it at all. You have to do what's inside here. So you would say, well, that's going to be the cosine of my function here, x cubed. And then you have to actually multiply it by the derivative of him. So you have to take the x cubed and take the derivative, which is 3x squared. So my answer for this one is actually going to be 3x squared cosine x cubed. That is the derivative. Find the derivative of the antiderivative is what they're asking for. It's, I mean, not to be overthought for sure. All right. So try that one. So when you did this one out, you should have gotten 2 over x to the 5th. You're just going to say it's 1 over x squared. I can't see it. Yep, x squared cubed. And then you have to multiply by the derivative of the x squared, which is 2x. So you get 2x over x to the 6th. That's going to reduce to 2 over x to the 5th.